Hello, let's take a look at roof structure, the first component of the roof element. And firstly, we are going to examine how we can uh, design or what are the important parts that create a load transferring roof. Um, in this video, we will be covering the concept of structure, load transferring roof structure and its pieces, how we can create these pieces out of timber and what will their properties be. The same issue, but this time we are going to examine the steel material. What will be the appropriate sizes and connections? Let's start with remembering the concept of structure that we discussed last semester, how the loads, all the loads that can affect a roof, including the wind, the earthquake, or the loads, the weights of the building products, or the birds or other things, snow, how can all these loads be transferred safely in a roof? Uh, I'm sure you remember, but let me refresh your memory. The structure, we can define it in these simple terms. It's the system which keeps the form of an object, any object, intact. Without this structural system, uh, the form of an object will not be holding and it will be deformed, such as this table. When we say table, we are of course referring this horizontal surface, and it's elevated from the surface of the ground, and that's the main form. We want that horizontal surface to be at that level without falling down, without changing its level. And when we are using the table, there will be certain things that we put on the table. Like if it's a dinner table, then we are going to put lots of plates and glasses, maybe, or silverware, and there will be food, and all of these things will create a certain amount of load. And if the surface, this in this example, it's probably it looks like a timber surface. If the surface cannot stand at that level under these loads, if it starts to fall down, if the level will change, or if it falls down and if it breaks into pieces, then it won't be able to function as a table anymore. That's what we need. We need it to be at that level without losing its form, without losing its level, and that's this. We need a system. That the system, required system, is the structure. And if you just remove the table top, we see that it has this object. And we can now transfer this same logic into the buildings. If we design a building in this form, then we need a system to keep its form like that. And there will be loads. And with the loads, there is this risk of losing the form, deformation. And that's something that we don't want. Again, like in the table, we can have a system, structural system like this. Or I'm sure you remember, in this example, we have a roof. It's the usual shape. It's in the usual shape, but the building is very interesting in my opinion. It's a floating building over the sea. And when we remove all the other things like the walls or the floors or the roofing elements, the windows, doors, and everything, we will be able to see the structural system that holds everything in its place. And we mostly create buildings or structural system as the skeletal system. In this example, we see its components. When we say a building structure, we are referring to the building element, and it has its components, such as horizontal beams or vertical columns, and the load transfer starts with the horizontal surface. In this example, we are referring a floor, obviously, and then the floor is connected or carried by the horizontal beams, and uh, under the beams we have columns, vertical components. The load will first be applied on the floor surface, and each floor will transfer their loads to the beams on their both sides or on two sides maybe, and each beam will transfer their loads to the columns on their ends, under their endpoints. That's how the load transfer happens in a skeletal system. For the roofs, we have the same logic. The only difference that can be the shape or position of this floor surface. You remember from last week's course, we can have flat roofs, and they are basically horizontal surfaces, no different than a standard floor in between different levels, stories of a building. It's a planar surface, it's horizontal, and it can be carried by beams and columns. Uh, it's the same thing with a normal floor. Uh, if we have an inclined surface only in one direction, or we can have more than one direction inclined sloping surfaces, that's the same planar surface, but it's not horizontal, it's sloped. And the same thing, when the loads will affect this surface, we still need a structural system under this inclined surface. As you can see, we have sort of, not horizontal, but inclined at the same slope. These components, they work like beams, and there are horizontal vertical components, just like the columns of the structural system, the same logic. Uh, Okay, now let's take a look how we can integrate the structure of the roof with the structure of the buildings, because when we design the structural component of the roof, we need to connect it with integrate it with the structural element of the building, because we want all the loads to be transferred safely to the building structure, and then the foundations, and then the ground safely. Otherwise, the roof will not be able to uh, hold its shape. We can have a simple example here. Let's take a look at this one. Let's imagine we designed a building, a very simple one-story building, and over that we had this shed roof. As you can see, we have this inclined surface, and this is cantilevered, the EU part, and that's the ridge part. And the sides and the ridge, they are restricted with parapet walls. These are called parapet walls. So we have this inclined surface. It starts at the ridge line and goes downwards with the slope till it hits the eve line. And just like the regular horizontal floors, instead of horizontal position, we can imagine the same thing as an inclined position. We will be needing beams, and then we will be transferring the loads of the beams to the columns. The same thing, the loads will be over this surface, and it will transfer their loads to the beams, like that. But instead of horizontal location or position, the beams will be inclined at the same slope of the roof. Here we have this example, and in the roof, as the roof structure, these pieces, each one of these beams, are called a rafter. Rafter, in Turkish we call it mertek. And first the loads will be over this inclined surface, and then that surface will transfer its loads to each one of these rafters. And under the rafters, we will be needing beams that work in the other direction. Here we have two of them. So each of these rafters, they will transfer their loads to the other beams. They are slightly bigger than the rafters, as you can see, because they will be carrying the loads that come from many of these rafters. We have a series of rafters like this, and each one of these rafters will transfer their loads to the beams in the other direction, positioned in the perpendicular direction. And these are horizontal. Only there is this level difference. This one is at the eave level. This one is at the ridge level. And these are called purlins. Purlins, aşık, aşık. In Turkish, it needs to be short, not aşık. If you say aşık, it's something else. It needs to be pronounced as aşık. Um, so each rafter will transfer their loads to the purlins. We have two of them here, and each purlin will transfer their loads to the vertical column-like structures. So we can, in this perspective, in this point of view, we can see one of these vertical column-like pieces, but the other one is blocked by this parapet wall. But we can be sure that there needs to be another one. Otherwise, this purlin cannot stand on its own without these vertical supports. And only one of them will not be enough. So we can be sure that behind that parapet wall, even if we cannot see it, there is another vertical column-like piece, and it's called stud. Stud for the roof, dikme in Turkish. And each purlin at that level, in the different level, here, that purlin is standing right on the floor. We have this floor surface, and it's the structural system of the start of the building. As you can see, this purlin here at the eave level, it's standing right on the floor. It's not elevated from the surface of the floor, so we don't need any vertical studs. But this one, it is elevated so that it will create the ridge line, and it's being supported with these two studs on each end. Let's take a look how it is, how we can see it if we are inside this area in between the rafters and the floor. That floor will create the ceiling of this living area on the ground floor. And over that, we have this triangular area. We are right now in between the rafters. As you can see here, we see a series of rafters, and we are on the floor, this floor area. So we have this inclined surface. It's made out of timber. We can see that first we have the surface, and then this surface transfers all its loads to a series of rafters, these inclined beams. And each of these beams, they are carried by slightly bigger beams, which we call purlin, in the opposite direction. And based on our design here, it's elevated from the surface of the floor, like this one. So the rafters will transfer their loads to purlins, and each purlin needs to be supported with studs, just like this one here. In this example, we see many of these studs, so we can say that probably this distance, this size is much longer than this example here on the drawing. So we need to learn about the limits and sizes. And on its two ends, we have two studs, and these are connected to the floor. So we can make sure that the loads will be transferred via studs to the surface of this floor. And we know that if it's a reinforced concrete building structure, that reinforced concrete floor will be carried by reinforced concrete beams, and each beam will transfer its loads to the columns. How can we create these rafters, purlins, and studs out of timber? We need to remember what we have learned last semester, the timber pieces and their properties. We are creating these pieces out of wood. And there are different types of wood depending on the tree and its properties. We can get different properties for the timber pieces, and we need to search for and prefer trees which give us timber that is durable against insects, microorganisms, water damage, and especially fire. We get this tree trunk and we saw it into different size of pieces, and we can use these pieces. These are called dimension lumber or kereste in Turkish, and based on the annual rings, we can have these lines which can be tight. The gaps in between these annual rings can be short, or we can have wider gaps based on the tree type and the growing conditions. That's what we are looking for. We need tight grains because these pieces will get lots of loads and they will work as the structural component of the roof. Narrow annual rings, closer the rings, the greater the strength. They will have a higher capacity to carry all these loads without being damaged. And of course, we are looking for a high density type of tree. Here we have different examples because the studs, the vertical pieces, they will be under this compression load. And if the properties of the tree cannot uh, stand or won't provide all these properties, it's not durable against insects, microorganisms, and if it gets damaged, uh, if there is water or humidity around these pieces or inside these pieces, or if there is a fire, then there is this risk of deforming and breaking into pieces. But if we prefer a high density tree with tight grains, then most probably it will have a higher capacity to stand against all these compression loads. And the rafters and the purlins, they are basically beams, so they will be under bending and deformation. They will be under these compression, and at the end of these compression loads, this upper part will compress, and the lower part will the molecules will want to be separated. That's what we call bending deformation. So for the compression, for the vertical pieces, and for the purlins and rafters, we need all these properties. There are many different examples, but we can prefer elm. That's kara ağaç in Turkish. It will give that kind of wood and timber. Larch, karaçam, and Calabrian pine or Turkish pine. We can see these examples. We can prefer these trees for the structural component of the roof. I'm sure you remember this part here. There's this thing that we call shrinkage. In Turkish, we say ahşabın çalışması. These pieces, when they are felled, when the tree trunk is being cut, they have a kind of sap or moisture inside them, and we let them dry, lose its humidity, and we know that it has these vertical pipe-like structure inside. That's how the tree emits all the necessary materials and water via its roots, and through these channels, that nutritions will be carried upwards to the leaves. And once we cut the tree and once we let it dry, the moisture and all the contents inside these pipe-like channels will be lost. And if we place this these pieces in a humid environment. When we say humid or humidity, we are referring as we are referring to the water in gas form in the air. All these empty channels will emit the humidity, the gas water in the air, and they will swell. And once the humidity levels in the air will drop down, all the water in the gas form inside these channels will be released back to the air around them. So they will shrink. Uh, but uh, in Turkish, it's called rutubet or nem. It's water in gas form. It's been misused in a wrong context, and many people they mix it. They say that the rutubet is the same thing with küf. There are two different things. When we say humidity, rutubet, nem in Turkish, we are referring the water in the gas form. So it's the water in the air. But when we say mold, küf in Turkish, it's a type of mushroom. It's something different. It's a living organism just like the regular mushrooms that we are used to, that we see in the natural environment, we know that it proliferates with spores. These are like seeds for the mushrooms, and once these seeds have uh, proper conditions of the nutritions and light and humidity and everything, they start to proliferate. They are creating new mushrooms. That's what we call a mycelium. And all these structures will create new mushrooms. Uh, Mold is the same thing. The only difference is they are so small. That type of mushroom is so small that it cannot be seen with naked eye. The things that we see here, these black things that we see here, it's the mycelium. It's already proliferated because that environment will provide the food, the required light and humidity for these tiny mushrooms to grow, to multiply. Normal conditions, it's microscopic and we cannot see them. But if they proliferate like that in this environment, a humid environment, they become visible. And since they are so small, since they are microscopic, they can be airborne easily. That's the normal timber form, but once it swells, once it emits all the humidity in the air, it will be deformed like that. And once it loses all its humidity when the air gets dry, as you know, that depends on the climate and the geographic location of the building. Sometimes the air gets so humid, especially if you are living next to in a city next to the sea, then you will notice that in the air there's so much humidity, especially during the summertime. Uh, so all this gas water in the air will be filling these channels. That's why it's changing its form, why it swells. But time to time, the air humidity level will drop down. The air will get become drier. At that condition, the humidity inside the timber will be expelled outside, and it will shrink in the opposite direction. Uh, and that depends on the position of these pieces that we create, where it is taken from the tree trunk. Uh, Here we have this example. That's the normal position or normal form of the piece, and this is the form that it shrinks. If we get a piece out of here in the pit part, it will shrink like that. If you get a piece like this in these dimensions and in this location, it will shrink like that. If you take a piece like this, it will shrink like that. And as you can see, these examples have a sort of uniform shrinkage. But if you take a piece out of here like this, and once it loses all its humidity, it will shrink like this. It's in non-uniform, especially as you can see, it shrinks so much and so abruptly, it will lose all its form, and that means it will lose all its carrying capacity. So we are looking for locations, positions where we have uniform or almost uniform shrinkage. We don't need to prefer, especially for structural components, structural pieces, not this part, not this part, not this part, because there's no uniform deformation. However, we can prefer the other parts like this here. Uh, if we take out, okay, I'm going to use this pen to draw something. If we prefer a piece like this, we can create, it's obviously a long piece like that, because the tree trunk, we have the tree trunk. We can use it as a purlin or a rafter, or instead of this rectangular shape, we can have a piece like this and use it. Again, it will be deformed like that, uniformly, mostly like this. And we can use it as a stud, or we can have this piece here, and we can create purlins and rafters, or a stud out of here, or this part. These are good positions and good shapes for structural pieces, for studs, purlins, and rafters, but we shouldn't prefer these ones because they shrink so much and they lose their capacity to carry all these loads. How we can protect timber? We need to protect all these pieces from water in liquid form or gas form, humidity, insects and microorganisms, and fire. That's a water damage. It causes the timber pieces to decay. That's what we call a wet rot, and this is how it swells. These are the timber pieces that have swelled due to water, liquid in liquid form. That's something. These are white ants. It's termites. Here in Turkey, in our country, we don't see them, but especially in the States, these affect timber pieces in a very bad way, especially structural pieces. You see all these dust-like things. They when you remove the shell or the piece, you will see that there's uh, nothing left behind. When we say fire, everyone knows that timber wood, these are combustible products or materials, and steel or reinforced concrete, it's non-combustible. You cannot burn steel or concrete. However, timber burns easily. But in case of fire, because of the high temperatures, very high temperatures, the steel is deformed like this. It melts down, and we see that reinforced concrete, the concrete will explode like that. So these are deformed in a bad way. However, timber will be protected if the sizes are correct and the type of the tree is correct, and we can enhance its properties against fire damage. And in normal conditions, the outer part of the timber will get burned, will turn into charcoal, and that thickness will provide sufficient uh, heat transfer, heat insulation, and the fire cannot get inside layers. So the timber piece will be protected. It burns, but it can stand. That's a very interesting example. After the fire, we see that the steel beams, they are melted down, but the timber beam, even if it's burned, even if the outer part will turn into charcoal, it is standing on its position. So everything, that's what we are looking for during the fire. The reinforced concrete and steel structure, there is a high risk of collapsing down because of that fire damage. But in the timber version, the timber pieces can stand so much longer than steel and reinforced concrete, and that provides us enough time to evacuate the users. And we can cover the surface of timber and enhance with these oils or organic solvents with different materials. We can use a brush to cover the surface, or we can spray these liquid applications, liquid coverings, or we can have this full cell or bethel process. In Turkish, that's what we call emprenye etmek. Here, all the pieces that are filled inside this high vacuum tank, and first they emit all the air, and then they apply that liquid, that chemical component. So all the channel-like things, the empty grains, they are filled with this chemical thing, and based on the type of the chemical that is being used to be absorbed by these timber pieces, it becomes more resistant against fire damage, against water and humidity damage, or the insects. So this is timber. How can we create these pieces out of steel? We can use steel pieces, obviously. Let's remember we have different types of profiles. W profile, wide flange. This is what we call the flange. These parts of the profile. And this is I profile or S profile from the standard profile, or N profile from normal. They are all same. It doesn't matter if it's I or S or N. They are referring to the same thing. Or instead of these I or W shape profile, we can have L shaped, C shaped, Z shaped, T shaped. We can have these sheets, and we can create our own studs or purlins or rafters, beams, by combining these sheets of steel in various positions. That's what we call a custom shaped profile. And we need to, again, let's remember from last semester's course notes, we need to provide protection, enough protection against fire damage and corrosion, especially when we are talking about the steel. In fact, fire and corrosion, they are both caused by a chemical reaction that is called a redox reaction. It's reduction and oxidation reaction. It's the short for reduction and oxidation, redox. It's the transfer of electrons between two different substances. Here we have an example, an element, and one of its electrons will be lost to the other element. That is the one that loses its electron, and this is the one that gains an additional electron. Loss of electrons, it will be determined as the oxidation. This material is oxidized. In Turkish we call it yükseltgenme. Bu materyal, bu madde yükseltgendi diyoruz. When it loses an electron, and a gain of an electron can be defined as reduction reaction. İndirgenme, that one that gains an electron, indirgendi. O madde, o malzeme indirgendi. It can occur between the oxygen atoms in the air and the atoms of the substances, such as this apple. When you cut an apple in half, or when you peel an apple and wait for a while, it starts to get brown. That's why the reason is because of the reduction or redox reaction. The electrons of an enzyme are transferred to the oxygen atoms in the air. So apple is oxidized and the oxygen is reduced. It can occur very slowly in case of, very quickly, sorry, in case of fire, or it can occur very slowly in case of corrosion. But the corrosion due to rusting. First, we have rust, and because of rusting, the corrosion, aşınma, chemical abrasion, kimyasal aşınma, bir tür kimyasal aşınma, it happens. Uh, how can we protect steel pieces against fire damage? There are paints that we can use. There are plasters, and we can use glass wool or rock wool. These are incombustible materials, or we can prefer gypsum. If we cover all the surfaces with these materials, then we will have a higher level of protection. The paints, they are called intumescent. Uh, First, we apply the paint and it's very thin, but during the fire, with the increasing heat, that very thin layer of paint will swell instantly and it will provide a certain level of heat insulation. That layer, that thickness, will provide a certain level of heat insulation. That means the increasing heat around this piece will not be transferred to the steel piece and it will be protected. The same thing can be done with the plaster. As you can see, it's thicker, or it's already thicker than the paint, much thicker because it's a mixture of different materials. There's this example, if you like, you can prefer that mixture, polystyrene, leave-in gypsum. You can spray it and cover all the surfaces of this profile. Glass wool, rock wool, it's like a thick blanket or thick carpet, very thick, like 3 centimeters or 5 centimeters, or in different thicknesses. And this thick thing, these boards are created out of glass or rock. We can have these volcanic special rocks. And in a factory, they are creating these very thin fibers, and they collect all these fibers and they create that board. But it's very soft, and you can easily squish it between your fingers, and you can create different thicknesses. And since these are made out of glass or rock, these are incombustible. That means you cannot burn them. And gypsum, again, it's very fire resistant. It doesn't get burned. In case of the fire, a gypsum board, that part has 1,000 centigrade Celsius. This layer inside the gypsum will drop down to half, and it's here 104 centigrade Celsius. And the other side, the side that covers these steel pieces, will have only 54 centigrade Celsius. So it will provide a very high level of heat insulation. By the heat insulation, the steel piece will be protected. Uh, for against corrosion, that's the rust. Uh, because of the oxidation reaction, rust is being formed. Pas in Turkish, paslanıyor. Sonra da bu paslanma nedeniyle korozyon, yani aşınma, kimyasal aşınma gerçekleşiyor. That's how the rust is created because of this redox reaction. A new chemical substance is being created and it just flies away. It vanishes into thin air. All these gaps is caused because of the flying away rust. That's the corrosion. We can use paints. If we cover all the surfaces with these paints, the electron transfer between the oxygen atoms and the steel atoms will stop, obviously. Or we can prefer galvanization. Instead of paint, we can galvanize the pieces. In Turkish, it's the same word, galvanizleme. Galvanizleyebiliriz. Galvanize çelik kullanabiliriz. How we do that? We have the steel profile and we dip it inside the melted zinc, and all the surfaces of the profile is being covered with zinc, and that layer of zinc will stop the electron transfer between the oxygen atoms. That's what we call galvanized steel. And the process is galvanization. In Turkish, we call it galvanizleme, and this material is called galvanize çelik. Galvanize çelik. It's been done like that. There's this bath, like a pool with melted zinc inside it. So they dip it. Or we can paint them with a coat of red lead aluminum paint. But we need to be careful about not damaging, not cutting, not drilling these pieces once they are galvanized or painted. We need to do all these processes before galvanization or painting. Otherwise, if we just drill it or cut it into different shapes, the paint or the galvanization, the zinc covering will disappear, and the surface will start to react with the oxygen. Or we can prefer stainless steel because stainless steel has chromium inside it, and the reaction between the chromium atoms and the oxygen atoms will create a passive protective film, and that's chromium oxide, and it's automatically being created. We don't need to do anything. Even if we cut it, drill it, change the shape, the oxygen atoms will react with chromium, and instantly they will create the passive film. That's why stainless steel doesn't get rust and corrosion due to rusting. We covered this topic too. Let's take a look at the sizes and connections. What are the required sizes and how can we connect these different pieces to each other? In this perspective, we don't see the inclined surface because it's been elevated, let's say, so that we can see the roof structure and all its pieces. These are the rafters. And for the rafters, if you prefer wood, we need to, since they are load-bearing pieces, we need to be careful about the shrinkage, the proper positions, and we can have a piece out of this tree trunk. The sizes, the required sizes needs to be okay, that's the dimension lumber. It needs to be hard and strong wood, like elm, pine, fir, or Calabrian pine, and the other examples. And that size needs to be minimum 5 centimeter, and that size needs to be minimum 10 centimeter, and the length of the piece can be in between 2.5 meters up to 3 meters. If you require a roof that longer than 3 meters, then we cannot just use one piece. We need to have two pieces, and we need to connect them like that. Let's imagine this size of the roof is more than 3 meters. Let's say it's like 5 meters. That depends on our design. That means I cannot have only one piece. I need to have a piece for like 3 meters or 2.5 meters up to here. And I need to have another piece and connect them on their ends like that. But if this distance is not longer than 3 meters, it can be 1 meter, 2 meters, 2.5 meters, 2.8 meters, up to 3 meters, then we don't need two pieces. We can have only one piece and place it in this inclined position to create one of the rafters. And as you can see, there is a series of rafters like that. They are positioned under that inclined surface. Or we can prefer, obviously, a steel profile with these measurements. Like again, it needs to be minimum 5 centimeters, and that can be 10 centimeters. But this length can change. This is for timber. We can have longer pieces out of steel, obviously. We can prefer box profiles, eye profiles, and the distance in between two rafters can be up to 45 centimeters or 50 centimeters. It can be shorter than 50 centimeters, but we shouldn't exceed 50. That's our upper limit. As you remember, last week we talked about that. If we are creating a beam, it doesn't matter if it's the horizontal beam in the building structure right under the floor body, or a rafter, a purlin in the inclined position. We need to prefer it like that, the shorter side and this longer side. If we have the same piece like this, positioned like that, it won't hold. The load-bearing capacity will decrease down instantly. That's why we need these dimensions. And here you can see that the rafters, they are over the purlin, and there are two of them. So we can call them, one of them, the upper one, ridge purlin, because it creates the ridge line. And in Turkish, it's called mahya aşığı. And the other one, the eave level, it stands right on this reinforced concrete floor, and we have the uh, reinforced concrete beam. Here again, we have a beam, so we have a high level of load-bearing capacity. We can just place it over the surface of the floor, and that's what we call a wall purlin, damlalık aşığı. If it's high at the ridge level, we can say that's a ridge purlin, mahya aşığı. If it's right on the floor and it's at the eave level, then we can call it wall purlin, damlalık aşığı. And we need a slightly bigger piece than the rafters. This size needs to be minimum out of timber and steel also, 10 centimeter, and that can be up to 12 centimeters. It's still rectangular shape, but it's bigger than, and the length, the total length of one of these timber pieces can be up to 4 meters. We can have 2 meters, 3 meters, 3.5 meters, and 4 meter is the upper level. And that is related with this design, with our design of the roof. If this size is up to 4 meters, then we can have only one piece positioned like that, like this. But if it is more than 4 meters, then we will be adding another piece so that we can have a longer roof. Just let's imagine it's the 4 meter level, and the distance between two rafters, between a wall purlin, sorry, purlins, two purlins, between a ridge purlin and a wall purlin, the length of the rafters needs to be maximum 3 meters. Why is that? Because that's the limit for one timber piece for the rafters. If it's longer than 3 meters, then you remember that if it's longer than 3 meters, then that's one of the timber pieces that I use for a rafter. And I will be using another piece like that so that it's longer, like 5 meter or something. And there are two different pieces like this. One of them is here, up to here, and the other one is up to there. And these pieces, they are supported with wall purlin, and they are transferring their loads directly to the building structure. And the upper part is supported with the ridge purlin. They can transfer their loads to the ridge purlin, but what about this connection? It's weak, so we can prefer another purlin here, right under the connections, so that this piece will be supported on its this end and that end. This piece, the other piece, will be supported on this end and on this end. And that can be called an intermediate inter mediate. I'm not sure about the spelling, but you understand. Berlin. Ara aşık in Turkish. If it's longer than 3 meters. But if it's just 3 meters, up to 3 meters, we don't need this intermediate purlin, obviously, because we will be using only one piece here up to 3 meters, so that it will be supported on this end and on this end. Okay, for the rafters, this is the limit for the rafters, 4 meters. Let's move on. Okay, I need to clean these things. Okay. Uh, that's an image that shows how we connect a rafter and the purlin. The connection, because of this inclined position, for the connection, we need to have these grooves for rafters so that it won't slip down over the purlin. And the purlin, each purlin, if it's elevated from the floor of the surface of the floor, then we need studs. Here, as you can see, the ridge purlin, it's been supported with one stud, and for the studs, we can prefer a square shape, like 10 centimeters to 10 centimeters. The height of this piece, it doesn't matter. It's not important because based on our design, it will obviously be shorter than 3 meters or 4 meters for the maximum limit. But each purlin needs to be supported at least with these two studs. And the distance between two studs needs to be maximum 4 meters. And that's as you remember, that's the required maximum limit for the length of a purlin. I can have a timber purlin for 4 meters maximum. And if my design is longer than 4 meters, then I need another piece here and another piece here. But each piece needs to be supported on one end and on this end. So this piece is being supported, and there needs to be another stud under that piece so that that end will be supported and this end will be supported. Again, the same thing can be applied to this end here. There can be another stud there so that this piece will be supported on this end and on this end. That's why the distance between two studs can be maximum 4 meters. It's related with the maximum length of a timber purlin. And that's why the maximum limit for two purlins is up to 3 meters. It needs to be shorter than that because the maximum length of a rafter can be only 3 meters. If we have a longer length than 3 meters, then there needs to be an intermediate purlin to support the middle part. And obviously, that intermediate purlin needs to be supported with studs on its two ends. Okay, we learned the sizes for a stud, but here you can see that there is a timber piece like a square plate, and that's what we call a bearing plate, yastık in Turkish. It is very similar with the foundation footings that we learned last semester. You remember that footing is this component of the foundations. Reinforced concrete column will transfer the loads to the footing so that the load will be spread. It will decrease with the footing. Same logic here. We have a timber bearing plate with 4 or 5 centimeter, thickness here, and each stud can be connected to a purlin, rich purlin or an intermediate purlin, uh, with the help of bracing. These are called bracings, göğüsleme in Turkish. These are again square section. These have square sections. They are inclined, and we can prefer 8 centimeters to 8 centimeters. They will just help the load transfer. The loads of all these rafters can be transferred. I'm going to change the color here. Can be transferred to the stud. But if you prefer bracings like this, they will help with the transfer. So we can use these pieces for bracings, and there are two thinner pieces next to the rafters, under the purlin, and next to the studs. These are called collars. If they have two of them on each side of the rafter, then we can say they are double collars because there are two of them. And their function is to connect a rafter, a stud, and a purlin, so that with the lateral loads like wind or earthquake, the system can be intact. Without these connections, without the double colors, but we don't need to do them on both sides. We can just prefer one of the sides. Then we don't need to call it double colors. Obviously, there will be only one color. The same logic. In Turkish, it's called çift gergi or kuşak. They are thin the timber pieces like this. We can prefer a 4 centimeter, and that can be up to 10 or 12 centimeter. The length, it's very short. As you can see, it's not important. There's no limit for that. Here we see an image. There is the stud and a purlin, rich purlin or in intermediate purlin, doesn't matter. And there is this rafter, and we can see that rafter is directly in position with the stud. Right under the rafter, there is the stud. But here we don't see that. These are only rafters without the stud. So these double colors or one color will be connected. That rafter, this purlin, and the stud, the three of them, like this. We can use bolts. That's an example for an intermediate purlin. That's the stud. These are the colors, and these are the bracings to help with the load transfer. That's how we can connect them. If we have these grooves, then it will hold in a better position. And since we are connecting the stud also, we can have little grooves, but we don't need to do that. If we do this and bolt them, it will hold in a better way, obviously. But in this example, you don't see any grooves. They are just nailed like that. And the same logic for the connection of bracings and rich purlin. We can connect the stud like that to the rich purlin. If you have this connection right under the purlin and the stud, it will hold in a better way. And here you can see the colors that are next to the rafter, like that, and they are bolted. We can use these thin steel sheets to hold the bolt, and that's how we can connect a bracing and the intermediate purlin or rich purlin. Again, we can groove them like this, or here in this example, they use these little pieces so that it won't, slip sideways. Or we can bolt them like this, uh, and the same thing for the this connection, the connection of stud and the bracings, like that. Here you can see the bolt. That's the bolt. These are grouped like that because we are looking for something like this. Here, if you drill a hole in this direction, like that, you can easily bolt it. You will use this bolt, and you can work in a better way. That's why it's being grouped like that. Okay, sizes and connections. We covered that. Uh, Hopefully next week we are going to talk about how we can express our structural decisions, how we can make proper decisions, and how we can express all these decisions via creating proper drawings. Okay, see you next week.